if we look at continuity, there are three definitions or three pieces we need to show for continuity. The first is that when we look at C, f of C exists. The second is that the limit as x goes to C of f of x exists. So if you think about the function, that looks like this. If we look at C, if we look at it from the left and from the right, the limit as x approaches C of f of x is out. If I now define that point and I say that f of C is out, they both exist. The limit exists, f of C exists. The third criteria is that number 1 needs to equal number 2. The limit as x goes to C of f of x is equal to f of C. All right? So f of C exists, it's some number. The limit exists, it's some number. If they both agree, then we have a continuous function. So let's have a look at discontinuities. We know about removables, also known as holes. We know what those look like. We come up, we have a gap, we don't have the function exist. So if that happens at C, the limit as x goes to C of our function, it exists, it's some number out, but f of C, this is our function f of x, we evaluate at C, we look for a value, it's undefined. They don't agree because one doesn't exist, so we fail condition 1, not continuous. What else do we have? We have infinite discontinuities. We think of those as vertical asymptotes. What does that look like? We have an asymptote. We probably have a horizontal. We look something like that. If we look at the C value, the limit as x goes to C of the function doesn't exist, right? We're going to positive infinity, going to negative infinity. It doesn't exist. So, not continuous. All right? So the two that we most commonly see are the removable holes, the infinite, which are the vertical asymptotes. All right? So, any questions on that? We look at our function. We look at x equals 2. We're going to have a problem at 2. Everywhere else, we're going to exist. F of 2 is 1 over 0. 1 over 0 is undefined. First criteria is that we exist at that value. We don't exist at 2. We're undefined, so we can end our test and state not continuous. We know a number over 0 is a infinite discontinuity, also known as a vertical asymptote, and it's at x equals 2. So our discontinuity happens where we are not continuous. It's at 2, and it's a vertical asymptote. Let's have a look at x squared minus 1 over x minus 1. Same thing we're going to look at. Does f of c exist? Well, is there any value here that's going to give me trouble? And it looks like 1, right? And at 1, I'm going to get 0 over 0, which is indeterminate, which does not exist. I failed the first part of my definition. So I'm not continuous. Now, we can look at that a step further. We know that f of x is x minus 1, x plus 1 over x minus 1, we know we can remove that discontinuity. Now, if we remove it, we now know that at x equals 1, pre-calculus lens, we have a hole. It's at x equals 1. When I plug it back into the remainder, I get 1 plus 1. My hole is more specifically at 2. If we wanted to look at the second part of my definition, does the limit exist? The limit, as x approaches 1 from the left, is going to be, once we remove it, 1 plus 1, 2. The limit, as x approaches 1 from the right of my simplified function, is 2. The left equals the right, therefore the limit as x goes to 1 equals 2. My limit exists, but my value at 1 does not. So I'm discontinuous at 1. We graphed it. We come in from the left, we're at 2. We come in from the right, we're at 2. Left side, right side. First criteria. Does f of 0 exist? Greater than or equal to 0, we're here. F of 0 exists, and we are equal to 2. Second criteria. Does the limit as x go to 0 of f of x exist? How do we show a limit exists? We look at it from the left. We look at it from the right. The left side of 0, I come in on the x plus 2 train, and I hit at 2. The right side of 0, I come in on the x squared plus 2 train. I hit at 2. The left side equals the right side. So the limit as x goes to 0 of f of x equals 2. Third criteria then. The function exists, it equals 2. The limit exists, it equals 2. It exists, limit exists, the limit is equal to the height. So we're continuous. So we can state, therefore, we are continuous because the limit at 2 is equal to f of 2, which equals 2. We need to state all of that for continuity. The function exists, the limit exists, the limit is equal to the function. All right? Left side of 1, we come in at 3. We don't exist. Right side, we come in at x squared plus 4. At 1, x squared plus 4 is 5. So we come in at 3, we leave at 5. Are we in the same place? No. Okay, there's a nice picture, but that's not enough to actually state it. So, 3 criteria. Does f at our problem area 1 exist? F of 1, this is where it exists, it's greater than or equal to, is 1 plus 4, which equals 5. Okay, criteria 2. The limit as x approaches 1 of f of x. Does it exist? Look at the left side. Limit as x approaches 1 from the left. Limit as x approaches 1 from the right. Left side, we come in on the 3 train. Right side, we come in on the x squared plus 4 train tracks. 4 plus 1 is 5. Do they agree? No. So does the limit exist? No. Limit as x goes to 1 of f of x does not exist. My function exists, it equals 5. My limit does not exist, therefore I don't pass both tests, not continuous. Alright, criteria 1, f of 3 needs to exist. 3 divided by 0 is undefined. F of 3 doesn't exist, first criteria doesn't get met, function cannot be continuous. Okay, if we took the limit, we should recognize that 3 over 0 is undefined, left and right limits. Let's look at that anyway. Limit as x goes to 3 from the left of x over x minus 3 versus the limit as x goes to 3 from the right of x over x minus 3. Now, we don't need to do this for continuity, but we should still be able to evaluate the limit. As we approach 3 from the left, I get 3. A little bit smaller than 3 is going to give us a negative 0. 3 divided by a really small 0, that's negative is negative infinity. 3 from the right, 3 over a bigger 0. Big 0, a small 0 that is positive is going to give us a positive infinity. The limits don't agree, therefore the limit also doesn't exist. The limit as x goes to 3 of f of x does not exist because the left does not agree with the right. Look at number 2. Does f of negative 3 exist? F of negative 3 is 0 over 0, which is undefined. We are done. We have not met our criteria. We are not continuous. But let's look at the limit anyway. Limit as x goes to 3 requires we look at x minus 3, x plus 3, over x plus 3 from the left. It requires we look at x minus 3, x plus 3, over x plus 3 from the right. We remove our discontinuity. We evaluate it. 3 from the left is, we're looking at negative 3. We're looking at negative 3. Is negative 3 minus 3? It's a little bit less than negative 3, but it's so little less that it's essentially negative 3, which is negative 6. Remove our discontinuity. Negative 3 minus 3 is negative 6. Therefore, the limit as x goes to negative 3 of x squared minus 9 over x plus 3 is equal to negative 6. Does it equal the height of the function? No. They're not equal. Therefore, we're not continuous. So, yes, we failed this one, right? We fail this. We don't have to do the rest, but it's worth looking at anyway. Let's look at C. Does f of c exist? F of 0 is 0. Let's look at the limit. Let's go to 0 from the left. Let's go to 0 from the right. Less than 0 is the left. Evaluate 0. It's 0 of f of x. If we look at the right, we're at 4. The limit on the right is equal to 4. The left doesn't equal the right. The limit as x goes to 0 does not exist. It doesn't exist. It can't match. Therefore, it's not continuous. Criteria. F of 6. 6 to the 4th plus 5 times 6 squared minus 3 equals 1,473. F of 6 exists. The limit as x goes to 6 from the right of our function, the limit as x goes to 6 from the left of our function. It's x to the 4th. It's going to be going up. I don't know, it's going to be doing something. You know, it could cross 0 probably. But we know it's 6, it's going up, right? So, let's look at what happens on the left side and the right